consider a second example. This is example 2.4 from your course text. And this is also on the evaluation of convolution sum through analytical means and both employing graphical means as well. So now, as a first example, let's consider two sequences. Now, the first sequence is x of n, that's the input to the system, and it's a finite length sequence, so it exists from 0 to 4. Okay, all the samples are unity, and it's 0 otherwise. So the impulse sequence is also given h of n, which is given as alpha n, where alpha is a positive, it has a positive value, and its magnitude is greater than 1. Therefore, it's a growing exponential from 0 to 6. Okay, so both sequences are of finite duration. Okay, other than the given indicated durations, they are 0. Okay, so these signals are depicted in figure 2.8. So here's figure 2.8 over here. You see x of n is all samples have unit magnitudes. So the samples, they exist from, there are 5 samples existing between 0 to 4. Otherwise, x of n is 0. Similarly, you have h of n as alpha of n, and this exists between n 0 to 6. Okay, and also given is that alpha is a positive quantity and alpha is greater than 1. Okay, so it could be 2 or whatever it is. But then you see that, for example, over here, the first sample is 1, then it grows. So this is alpha squared. Okay, and this trend continues since alpha is a quantity which has a magnitude greater than 1, and so this trend continues. So dot 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 dot. Last will be alpha 6. Okay. All right. Now, if you recall, so in order to calculate the convolution of two signals, it is convenient to consider 5 separate intervals. And okay, so we'll get to figure 2.9. There are 5 intervals. So graphically, there's a way to see this convolution graphically. But first, if you recall the convolution sum, which is given by the system is LTI, then the output y of n is given as xk, which is my input as a function of k, multiplied by the flipped and shifted version of the impulse sequence h of n minus k. So if you look at the definitions of your sequences, this summation is over k. Okay, so you must know that you have to multiply the sequence. For example, if you have to evaluate the sequence at y of n, then h of minus k has to be shifted by n number of samples. N could be positive or negative. Okay, it's an integer. So, so what is the expression that I have? Well, this can be expressed as summation over k. X of k, all the samples are identically equal to unity. Okay. However, hn minus k can be written as alpha of n minus k. Okay, alpha of n minus k. Now it depends, since the summation is over k. You can take alpha n outside the summation, and you're left with alpha minus k, and then you can sum it up. So but before we do that, let's consider figure 2.9, and let's have a look at the 5 separate intervals for n. So this is your figure 2.9. It shows the graphical interpretation of the convolution performed in example 2.4. So what it says is that x is a function of k, exists between 0 to 4. Then you have hn minus k, and for negative values of n, okay, when n is less than 0, there is no overlap. So this implies that for n less than 0, so for n less than 0, since there is no overlap, your since there is no overlap of xk at h of n minus k, y of n is 0. Y of n is 0. So for n less than 0, this implies that y of n is 0. You don't need to consider the values of the output of the system for n less than 0. So this is 0, right? Similarly, let's have a look at part F first. This shows for n greater than 10. Okay. You also note that in all these figures, this is n minus 6 up until n minus 6. So this should be n over here. Okay. Then you have n minus 6 to n. That means there are 6 samples. So we're already considering 6 samples, but we are considering this in the flipped way. Okay. So this is all h minus k flipped by n number of samples, and n could be anything, any value which up until where you want to evaluate your output. Okay. Now, if you see for n greater than 10, so the least value could be, for example, 11, let's say. Then 11 minus 6 is 5. Okay, that's the least value. Then 5 has no overlap with x of k. Okay, so that also implies that y of n is 0. This also implies that y of n is 0 for n greater than 10. Okay, so for n greater than 10, your output is again 0. Okay, now, so this is what these two figures imply. Okay, this is what these two figures imply. Now you are left with, so these are my 5 intervals, 1, 2, 3, 4, and 5. Now let's have a look at these 3 intervals. Okay, so analytically and graphically, what it means is, now over here, your n is varying from 0 to 4. Okay, so this is my n, and its value is ranging from, so the minimum is 0, and you can go up until 4. That means if you write this expression analytically for interval 2, for interval 1, we know that for n less than 0, there is no overlapping, so no non-zero, but there is no overlapping between the non-zero portions of xk and hn minus k. There's consequently y minus 0. That's my first interval. Okay, so this is evident. Now, for interval 2, we are considering this n. Okay, this is the flipped version of h minus k, and n is varying from 0 to 4. So my expression xk h of n minus k is given by alpha n minus k, and k has to vary up until n. Okay, and n is varying from 0 to 4. So k starts with 0 and ends up until n. Now, if you recall this expression, you see k is 0. Why k is 0? Because it has to start with the first sample of xk is 0. Okay, so, and this overlapping is up until n, which is a variable. Okay, so whether it is 2 or 3 or up until 4, we don't know that, but in this range, so k starts with 0, because less than 0 there is no overlapping, but for 0 and greater than 0 up until n, we have overlapping sample. Therefore, we have this xk hn minus k, that's alpha n minus k. Then we can evaluate this sum using a finite sum or geometric progression formulation. So specifically changing the variable of summations from k to r equal to n minus k, we obtain, so you can, if you replace this as r, and then you have this starting with k equal to 0, n is also from 0 to 4, so you have this from 0 to n. Okay, so this becomes a geometric progression. This is 1 plus alpha squared, so you have this formulation. Okay, so this is for y of n for n 0 to 4. Okay, for n 0 to 4. I mean, what it means is you can put those values, either you can put 0 and it will produce 1. Okay, so if n is 0, then you have only one non-zero overlapping sample. So multiplied by xk is just unity, right? So you see over here, for n less than 0, this is identically equal to, well, this is identically equal to unity. Similarly, if you want to evaluate this for n equal to 1, then you have two non-overlapping samples. So this produces, for y equal to 1, for example, this becomes equal to 1 minus alpha squared over 1 minus alpha, which is equal to 1 plus alpha. Okay, so you can use this relationship for either you do this graphically, or you can write the analytical expression for the sequence multiplications and then sum it up for all k. The result will be the same. Okay, so you can use this relation for 0 to n equal to 4, and you can see this for y equal to 1. If you have to evaluate this for y equal to 1, there are two non-overlapping samples. The first sample is 1, and then you have alpha, so 1 plus alpha. The first sample will be multiplied by 1, the second is also 1. Okay, so over here you have two samples, and one would be 1. The first sample would be So you have two samples, so 1 plus alpha. Okay, 1 plus alpha will be the result. Um, okay, so this is, let's go to table 3. It says that n is greater than 4, but n minus 6, the last sample, is less than or equal to 0, which implies that you are asking for a range of n from 4 to 6. Okay, so so that means again your x of k hn minus k is again alpha n minus k, and it has to vary from 0 to 4 because 0 to 4 is the overlapping range. 0 to 4 is the overlapping range for xk. Okay, so for this range, for n between 4 and 6, you have to start with 0. That is from where the overlapping starts. And whatever is the maximum value, it has to be between 0 and 4. Okay, it doesn't matter if your one sample goes out, you don't need to consider that. Okay, if that is greater than if this is outside your range of vision, which is from 0 to 4, you forget about this. You forget about whatever sample you have below 0. So your summation has to start with 0 and up until 4. That is the range of vision for xk. Okay, it's the range for xk. And then you evaluate this formulation. Again, we use the geometric sum formula to evaluate the above summation, specifically factoring out the constant of alpha n from the summation. This is alpha n is out. And there are 5 samples. Okay, so this is alpha minus k. So you have 5 samples. The ratio is alpha inverse. And then you can write this up as like this. Okay, so this expression holds for n between when n is greater than 4 but n is less than equal to 6. Okay, then there's a fourth interval. This is my fourth interval, which says that n is greater than 6 but less than equal to 10. Okay, so again, it has to start with n minus 6. N minus 6 is the last sample in the flipped h minus k. In the flipped h minus k, my last sample is, I mean, it starts with n minus 6. So it's not the last sample, it's the first sample. So it starts with the first n minus 6 sample and goes up until 6 more samples up until n. So the length is intact. Okay, the length is intact. But n minus 6, as it says, is over here. N minus 6 is less than equal to 4, but n is greater than 6, which means that n is varying from 6 to 10. Okay, therefore k so the first sample n minus 6 has to be within the same range of vision. So my upper limit has to be 4. Okay, why the upper limit has to be 4? Again, because 4 is where my x of k has the last non-zero sample. Okay, beyond this I don't care because the samples are not overlapping. Okay, so it has to start. So whatever this index is, this is n minus 6. Okay, n has the given range of vision. Okay, the range for n is given, but my range of vision for xk is fixed, so the upper limit has to be somewhere, wherever it is. Okay, so the upper limit is 4, and that's where I'm considering. Okay, so it has to, so k has to start from n minus 6, and it has to go up until 4. Okay, so again the same expression alpha n minus k, and using the same summation formulation, and to change the dummy variable to r equal to k minus n plus 6. So over here it should make this as k minus n plus 6. Then you can see that r starts from 0. R starts from 0, and you have this up until over here. If your k is 4, okay, so k is 4 over here, then it comes 10 minus n, 10 minus n, and then you have alpha n minus k, which means r minus 6, or you can write this as 6 minus r for n minus k. This is the other way around. This is k minus n, this is n minus k. So this becomes 6 minus r. So this is alpha 6 if you take this out, and then you have alpha minus r. So this varies from 0 to 10 minus n, and this is alpha 6. Okay, alpha 6 is out, and summation is over r. Use the same geometric formulation, and then you end up this for the expression for y of n, which varies from n minus 6. This varies from 6 to less than n, 6 is less than n, but it is less than equal to 10 as well. Okay, n is greater than 6, but it's less than equal to 10. Okay, so this is the range for y of n. And then in the last interval for when n is greater than 10, there's no overlapping. This is 0. So this is pictured over here. This is my output, and there are 5 intervals which are given as such. For n less than 0, y of n is 0. For n greater than 10, y of n is 0. For 0 to n4, we have this expression. For 4 to n4 to up until 6, evaluated the geometric progression as alpha n minus 4 minus alpha n plus 1 minus alpha. For 6 to 10, we have this expression. Okay, so this is a summary. Okay, this is what we obtain. And this again, you see what is happening is you don't consider your output y of n for n less than 0, but you keep on sliding your flipped impulse sequence from x of k, and you see what happens is that as you are summing it up, as this sequence it keeps on flipping. Okay, so this is the flipping of h minus k and sliding flipped, and this is the sliding of the sequence towards right. The samples, they first grow. Okay, because first you accumulate. So graphically what is happening is as this sample, this small sample of this sample, this first reaches over here, then this is your output y of n, something like this. Okay, and then from 1 it grows to, let's say, 1 plus alpha. Okay, and then it keeps on growing. So then it keeps on growing like this, dot 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 dot. So this is where the maximum number of samples have been overlapped, and we have summed it over k. And then when this n minus 6 sample leaves, so this is again sliding. You're sliding this towards right. So it starts decreasing. Okay, since the number of samples, overlapping samples, have been are reducing, the overlapping samples are reducing. So the general trend will be like this. It increases and then it will decrease. So this is what you see over here. So it increases first. This is the sample where the maximum number of samples for both x, k, and h of n minus k are overlapping. Okay, and then again over here, the number of samples or overlapping samples are decreasing. So overlapping samples are decreasing this way. So this is my xk. This trend is being defined by the summation xk hn minus k multiplication and summation over k. This is my y of n. Okay, and the highest sample shows where the maximum number of samples are overlapping. This is the sample where in the output y of n, where you have the maximum number of samples overlapping between xk and hn minus k. And then as hn minus k is being slided, you see the number of samples are decreasing, and a point comes when n becomes greater than 10, and is 11, there is no overlapping, so it becomes 0. Okay, you can see the 11th sample is 0 over here. 11th sample is 0. So for n greater than 10, your y of n becomes 0. And this is the same case for n less than 0 because there is no overlapping. But in between where there is maximum overlapping, there is a maximum sample. But since you're sliding this down, the sequence xk, your y of n is decreasing. Okay, so that's how you look at it at the scenario graphically. But analytically, if you have to write the samples, you have to evaluate the samples. So you can write this from geometrical formulations, considering the geometric progression in each interval. But you have to be careful how you decide this on for k variations, okay, given the range for n. Okay, so that's all.